One of the non-intuitive aspects of space is that things in it don't really have locations. They are constantly shifting where they are relative to Earth, and usually at very high speed. Lagrange points are the rare oases, stationary islands in space. As a result, they are invaluable real estate. Space is huge, but only a couple places are static in relation to Earth. One is any object in geostationary orbit, a ring of space 22,000 miles above the equator, where the orbital period is exactly once every 24 hours. Objects they orbit at the same rate our planet spins, thus appearing as if they hang right overhead. This is a tiny little ring around our planet compared to Earth's total orbital space. It's currently pretty full and getting fuller of geostationary satellites, so that space is very valuable. But there's another region of interest to us today, indeed 10 of them, called our Lagrange points, and these points are unique for being stable places that don't move relative to the bodies they are connected to. Today we'll be discussing them, how they function, and what value they have. They've already proven themselves useful. The James Webb Telescope is at the Earth-Sun L2 Lagrange point, or in orbit of it to be more precise, because that keeps the Earth between the telescope and the overwhelming glare and noise of the Sun. The Lagrange points of any two-body system orbiting each other, like Earth with the Sun or Earth with the Moon, are spots where the gravity of the two bodies causes a pocket that will move with them. Normally an object closer to the Sun will orbit it faster, indeed not just by having a smaller circumference to orbit by virtue of being closer, but actually moving faster too. Venus orbits at 35 kilometers per second, compared to Earth's orbital velocity of 30 kilometers per second, or 18.5 miles per second, and it orbits at 0.7 AU, 70% of Earth's distance, so it moves 17% faster than Earth and has only 70% of the distance to cover. As a result, its own year is 225 of our days, instead of 365. Amusingly, that's actually longer than its own day length, which is super long, and as a result, Venus's equivalent to geostationary, venostationary, would be around 1 million miles from it, much too far for a stable orbit, and further from it than its L1 or L2 points. We will dip into Lagrange point mechanics as we go, but the L1 Lagrange point is the one directly between two bodies where another object might be placed and stay in that same spot between them, while the L2 is on the outside, just beyond the second body, and the L3 is way on the other side of the other body, with the L4 and L5 points forming equilateral triangles with the two orbiting bodies. Stuff can be put in Lagrange points and expected to remain there with only a minuscule amount of station keeping. You can think of Lagrange points as where things can essentially hang out at the edge of the two bodies and their competing gravitational influence, rather than specifically orbiting the smaller body, even though L1 and L2 are much closer to that smaller body than the larger one. Indeed, the distance to the L1 or L2 point of a smaller body that is orbiting something much more massive is essentially the end of where anything can orbit it without losing that satellite to its own parent, also called the Hill sphere. For anything tidally locked and slow turning like most moons would be, the L1 and L2 are a great place to put a terminus station for a space elevator, as they don't have proper geostationary spots themselves due to their slow rotation and the proximity to that bigger body they orbit. Now, your necessary orbital velocity is related to how strong the gravity is that is pulling you, so the outer body pulling on you is going to slow your necessary speed, and indeed it needs to be lower than where that body itself orbits at because you still have a shorter orbital path or circumference by being closer to the Sun. Something at our L1 point has the same orbital period as Earth, but moves slower in velocity than Earth does, as it has a smaller orbital path. The reverse happens at L2, where Earth is in the same direction as the Sun and adds its gravity, so that orbiting body needs to move faster to counteract it. Normally it would orbit slower than Earth by being further from the Sun. This isn't very stable, and tiny perturbations like the orbit you're on being an ellipse, not a circle, which it is, or having neighboring planets yank on things, which they do, can destabilize these spots. but what it means is that there is a spot about 1% of the distance from Earth to the Sun, and 1% further from the Earth out from the Sun, where you can mostly stably orbit along with the Earth every 365.25 days, and where your orbital speed is about 1% lower or higher than Earth's. L1 is not where gravity is zero between the Earth and Sun, even though people tend to assume that's the case. That spot is much closer to Earth, around 156,000 miles or 250,000 kilometers from Earth, and closer to us than the Moon, whereas L1 is almost 6 times further away and 4 times further away than the Moon. That 0G spot would be calculated by taking the square root of the Sun's mass relative to Earth's, and that is the fraction of the distance from Earth to the Sun. Only when two bodies are identical in mass is the L1 also a zero gravity spot. I don't want to dip into the math, but if you're curious, in cases where one of the two bodies is way more massive like the Sun is to Earth, by a factor of 330,000 to 1, the L1 is the fraction of the distance between them equal to the cube root of a third of their relative mass, rather than going with the square root, and again for Earth and the Sun it's about 1%. For a body about 3,000 times more massive than its satellite, like the Sun is to Saturn, it would be about 10%, so the Sun, Saturn L1 and L2 are 90% and 110% the distance out to Saturn, roughly 1 AU or astronomical unit, as big as Earth's own distance from the Sun. The approximation breaks down as they get closer in mass, and the Moon's L1 and L2 are about 16% of the distance to Earth out from the Moon. Two obvious uses of L1 and L2 are solar shades and mirrors. If I want to limit the light hitting Earth to cool the planet, I can put some mirrors or even debris up there to filter some light out at L1. That wouldn't even be noticeable on Earth, even ignoring that you can't stare at the Sun to see them, and indeed you might simply pick some material that was transparent to visible light but absorptive or reflective to near-infrared, which is a lot of the light we get from the Sun, and which has no real use in photosynthesis. It is also so far from Earth that only a minuscule fraction of the radiation inbound to Earth that they intercept would go on to hit Earth once they re-emitted it omnidirectionally as black-body thermal radiation. It's a decent place to build power collectors or space farms potentially too, but I think any civilization with our basic orbital mechanics is going to eventually put up a number of devices at L1 to help protect them from irregularities in sunlight. You could potentially mitigate damage from a solar flare or even a full-on coronal mass ejection with a system in place at L1. You could even stabilize the light you have coming in and filter frequencies to eliminate changes over the year for a planet with a more eccentric orbit, or to remove a lot of infrared light and replace it with more visible light or photosynthetic light, very handy for terraforming planets. Scale can be deceptive in cases like this. You might be thinking of some huge L1 megastructure, and you might indeed build that one day, but you really don't need to. Instead, imagine a bunch of simple satellites with a lot of reflective paneling no thicker than tin foil, with just a bit of wire and computers for turning themselves and a small solar panel. That might mean a control module weighing tens of kilograms for a panel maybe massing 10 times that, and a few kilometers across. 1,000,000 tons worth of those, or 10 aircraft carriers worth of material, would easily affect 1 or 2% of the sunlight coming in to get Earth. That's just not much mass, and nothing sophisticated either. It's way less than a single modest O'Neill cylinder would take to build, and would be comparable to a Kalpana 1 space habitat, and you might have several of those habitats stationed out there by then, tending to them, and receiving the occasional kinetic shove from them for station keeping of its own. These devices are effectively LIGites, a mix of a normal satellite with a solar sail-style static satellite, or statite, that can hover directly over any spot of a star without needing to orbit. See our recent episode on statites, LIGites, and quasites for more discussion. Instead, they have a very tiny power supply and they twist themselves to bounce light in a given direction, or if opaque on one side, absorb it instead of reflecting it, and maneuver themselves around for station keeping. They could rotate like a piece of paper to expose a maximum cross-section or a minimum one, and through this you could control how much light came through, and again in the frequencies of your choosing. The application alone makes L1 some very valuable real estate for Earth, but it's even better for a place like Mars, where some solar-paneled electromagnets at the L1 can mimic a powerful magnetosphere for Mars, preventing incoming solar wind and ionized particles from stripping off any atmosphere we add to the red planet. At the same time, it can basically make the sun a bit bigger and brighter there by having some mirrors just to the side of the light coming to Mars to bounce some more adjacent light on the planet to warm things up in a visually natural way. Now, on tidally locked planets like those around a red dwarf star that would be eternally lit on one side of the planet and eternally dark on the other side of the planet, we can have a big eye open and close to permit day and night cycles on the sunny side, and we can stick a big mirror behind the planet at its L2 to collect light and blast the dark side with it. In practice, I would imagine this would be millions of smaller satellites, and I would also imagine they'd spend their night cycles bouncing that light to various power collectors or space facilities. And again, any celestial body has Lagrange points. Thin panels can function as solar sails or laggites to provide station keeping and even fairly heavy maneuvering, so we need not worry about L1 stability as much. That means you could put a huge parabolic dish array behind a planet and bounce light down onto it to thaw it out. As we already noted, solar L2 is a good place to shield something from sunlight when it's a planet's L2 with its own star, and again a place we like to put telescopes. A planetary L2, like the Earth-Moon L2, is a way to shield against planetary noise, and a place that will almost always have sunlight so that it can consistently generate power. Planetary L2s are a good place to hide spycraft, particularly those in an L2 orbit who just peek out from around that moon to look at you and then send a tight beam signal off when you're in the shadow of that moon. That's probably only useful for spying on early civilizations before they get to the Apollo program level, and truthfully only valuable for maybe 1 or 2 centuries while they've got real telescopes but still aren't into space. Another place that is like that is the solar L3 point, or the counter-Earth position. L3 actually isn't quite a counter-Earth spot unless the object at it was also Earth mass exactly. It's on the exact opposite side of the Sun as we are, and you might wonder why we even need to concern ourselves with Earth's own gravity at this point, since it is so tiny compared to the Sun's, and if we were talking about anything other than long timescales, astronomical ones, we really do not need to care. Here, the Earth is pulling in the same direction as the Sun, same as with the L2, but it's way further away. The Earth-Moon L3 is a bit different. The Moon is much closer to Earth's mass, and thus the Earth-Moon L3 is 99.3% of the distance the Moon itself is, in the opposite direction of course. Why it isn't stable is exactly because of that slight pull of Earth, or the smaller orbital body, and explains why anything off-axis, say 170 degrees instead of 180, is even less stable. As we'll see, in a perfect two-body system, where the big ones are in a circular orbit, you only have 3 points of stability on that orbital path, the L3, L4, and L5, at 180 degrees, and then 60 before and after, the Trojan points, which we'll get to shortly. Our L3 with the Moon has no special value that I've heard of or thought of, short of a Kepler-Rosette scenario where multiple celestial bodies are placed so their gravitational pull effectively cancels out. I think it would be a stretch to argue for 2 moons in their mutual L3 spot, but with lower mass moons it's semi-plausible. For our world builders and sci-fi writers out there, there's a lot of interesting multi-moon scenarios involving orbital resonances or L3. For counter-Earths, this is an idea that goes back to the dawn of science and maybe even predates Socrates, and showed up in a fair amount of fiction before we started sending probes off to deep space. In truth, I don't know if we ever actually trained a telescope on the counter-Earth spot to see if there wasn't a planet there, but it doesn't matter if we actually looked or not. We could already have detected it gravitationally. The High Evolutionary from Marvel Comics, best known from the Adam Warlock plotlines, is often situated on a counter-Earth, and in the old days, Superman's homeworld of Krypton was located there, making the idea of him being desperately crammed into an escape pod by his parents a bit more plausible. The fictional planet of Gore is also set there from John Norman's Gore Saga, though I don't recommend the novels. We also have the planet Mondas in Doctor Who, the homeworld of the Cybermen, and that's a counter-Earth, and they also show up in the Godzilla franchise. It makes some interesting fictional scenarios, but at the end of the day, there's not much real value there. It is the one place you can plausibly park something of reasonable size where a modern civilization like ours still isn't likely to see it. You're not likely to see a mile-long spaceship or even a larger station there if you just happen to be glancing in that direction with a probe halfway to Mars. And it wouldn't be a bad place to try to sneak up or spy on a new colony planet in another star system, except it also wouldn't be likely they didn't have any space capability themselves or wouldn't think monitoring that spot was a good idea. Usually best not to hide in the place everyone would expect you to. Indeed, to move on to the Trojan points, the L4 and L5 Lagrange points, you are almost bound to have relays or telescopes at those spots, and they could very easily glance at the L3. Back when we were first getting decent at spotting asteroids too small to qualify as a dwarf planet, we noted there were a ton of them orbiting about 60 degrees before and after Jupiter took in its orbit of the Sun, and those got named for various characters from the Trojan War, with a Greek camp and a Trojan camp. The L4 point is the Greek camp, orbiting ahead, and the L5 Trojan camp behind. These points, L4 and L5, and around other planets too, have come to be generically called Trojan points. Probably since there's no existing country of that name we might get confused with in conversation. The National Space Society, the organization I currently have the honor of serving as president of, was made from combining two separate space advocacy groups back in the 1980s, Wernher von Braun's National Space Institute and the Gerard K. O'Neill-inspired L5 Society. And while I have not found anyone who knows for sure why L5 was picked over L4 for a name, both are equally handy, it is specifically the Earth-Moon L5 that the L5 Society and the NSS are referring to. Now, if you draw an equilateral triangle, one where each corner is 60 degrees and each side the same length, and put your two bodies at each corner, the Earth and Moon in this case, the other corner is your Trojan point, and if you flip it around you'll get your other Trojan. These are fairly stable spots, and indeed represent a fairly large region where things can orbit without too much perturbation by the two bodies. Logically speaking, the distance separating them from those two bodies is very large, the same as by which they separate from each other, and the Moon doesn't exert much force on us. The Moon is around 60 times further from Earth than we are from Earth's center, and masses an 80th as much, and so the force it exerts on us, or some Trojan object, is about 3 parts per million of what a falling object on Earth's surface experiences. But that's not trivial either. It means over the course of an entire day, with 86,400 seconds, the object would have gained nearly 3 meters per second of speed towards the Moon, and after a year gained fully a kilometer per second of speed, and as it gets closer it experiences considerably more force. At 30 degrees ahead instead of 60, being half the distance, it then experiences 4 times the force and acceleration. That force isn't directly backward along the orbital path though, so an object being dragged this way does not necessarily crash into the smaller of the two bodies. It could crash into it, it could end up as a small moon in orbit of it, and yes, moons can have moons of their own, or it could get ejected into a different orbit. Eventually that object will cease being there, though at the larger solar scale, those planetary Trojans like Jupiter have are pretty stable, especially as its gravity is so large compared to other planets nearby that have the potential to cause perturbation. You wouldn't get many naturally occurring Trojan asteroid collections in inner systems with rocky planets like ours. They would perturb each other too much, and this effect is why we tend to refer to Jupiter as the solar system's vacuum cleaner, sucking debris up in its wake. This is why things can't share an orbit with us around the Sun or the Moon around us. They get yanked out of the path by the mass of the other body. Our Lagrange points are the stable points, marginally, because a balance of forces occurs there. At solar L4 for instance, that body is being pulled backward by Earth while the Sun pulls it inward, but it's not actually backwards. It's forming not a right triangle between Earth and the Sun, it's 60 degrees, so Earth is giving it some push in toward the Sun too. For the L5 point, Earth would be increasing the gravity pull inward to the Sun by a bit, raising the needed orbital velocity, while also yanking on it to drag it along. It can be hard to get an intuitive feel for why this is stable, but if it were a bit closer than 60 degrees, there would be a small force pulling it toward Earth and also outward from the Sun, and the reverse if it were more than 60 degrees, and similar effects for if the object at the Trojan point were closer or further from the Sun than Earth was. And again, the same applies around the Earth-Moon system, which is also way smaller and way more evenly balanced in mass, the Moon being a bit over 1% of Earth's mass, while the Earth is a few millionths of the Sun's mass. So this means that if you're seeking any stable arrangement of space stations or facilities that aren't very close to either Earth or the Moon, you have huge perturbative forces to deal with. And those Lagrange points come in very handy as places where those are reduced to nearly zero. It is where LIGITEs also come in as very handy options, and why I often talk about space stations being larger facilities with one or more rotating habitats at their center and larger collections of lighter facilities in a constellation around them, and the bigger solar collectors and mirrors being on the outskirts of that. They not only serve as some shielding for the inner region, paper-thin though they are, but they can function as LIGITEs, and ones with fuel-free maneuvering ability. At Lagrange points though, the mass to cross-section ratio can be a lot more generous than normal. Sunlight exerts force via radiant pressure, but it's very minimal compared to what we normally need for rockets. It is on order of about 1 Newton for every 10 hectares or 25 acres of sail, or about 10 newtons for a square kilometer. That's about how much force a single kilogram of matter experiences from gravity on Earth's surface. We can make materials thin enough they would be a square kilometer wide and weigh just 1 kilogram. That's the key aspect of solar sails and statites, but if I have an object as far from Earth as it is from the Sun, then it's only experienced about 2 billionths of the normal force of gravity from Earth that it would be on our surface, and it doesn't take much surface area per kilogram to counteract that force now. Enough that a regular-sized object might just need to be shiny and able to rotate itself to manage station keeping anywhere along that Earth orbit, especially closer to the Lagrange points, and you could mimic Lagrange points in a much wider volume with that LIGITE approach. This is our reasoning when we discuss what we call a Terran ring on this show, a huge collection of space habitats and facilities in a wide torus around Earth's orbital path, such that it would look like a ring with Earth as its gemstone. Simple high-strength tethers running between all those facilities would allow easy station keeping, in conjunction with some other tricks we've discussed over the years for moving momentum around in a careful and calculated fashion. Some like telescoping or tethering bits together we examined recently in our episode Orbital Defense Platforms. As another example, if I have 3 objects, one at a Lagrange point and one a bit further from the Lagrange point, and one a bit nearer, I can connect a physical tether to those with a winch and just pull things a bit one direction or another to counteract any perturbative drift. Especially if one of those anchor objects had a big solar panel or unfoldable sail it could expand when needed. I suspect you would often fold those up too, as they are going to take a lot of wear and tear from micrometeors and space dust while expanded or inflated. Closer in for the Earth-Moon Trojans, that is a higher bar, as while the Moon's surface gravity might only be a sixth of Earth's, its Trojan Lagrange points are only about 200 times further from its center than its surface is, so gravity is about 300,000 times weaker there than the Earth's surface, around 33 micronewtons, as opposed to the Earth-Sun Trojans, 500 million times weaker at about 20 nanonewtons. That very much alters the size we can contemplate for LIGITEs and makes those lunar Lagrange points pretty important to future development, though again we wouldn't think of them as points but rather regions. The difference in lunar gravity from being at the L4 or L5 point and being 4,000 miles away is a few percent weaker or stronger and on an order of a micronewton per kilogram or whatever it's pulling on. Again, in space where there's no air drag or resistance, that can build up pretty quick, but it could still be counteracted by the equivalent of 1 square foot of solar sail, and that's such a tiny force that even a cable made of relatively mundane and weak materials thousands of miles long would not snap under the load. In other words, that means you have a region at least as big as Earth, if not bigger, in which to be putting facilities. And this is 3D, not 2D like our planet's surface, and they're not moving at high speeds relative to each other like stuff in low Earth orbit is moving, where objects moving opposite directions will collide at as much as 16 kilometers per second, or 10 miles per second. Indeed, the moon's orbital speed around Earth is just 1 kilometer per second, so even a maximum speed collision of two objects counter-orbiting Earth out there, which there is no real reason to do incidentally, would involve 64 times less energy in such a collision. This volume, once full of megastructures, might also expand by them having some amount of gravity themselves, and again there's no reason to counter-orbit or be orbiting at steep angles compared to each other, and this gives us another reason the Lagrange points are appealing. There's no Kessler syndrome scenarios there. Cascade debris situations involve the idea that an object gets hit and blows more material off, and that material is moving slower now than whatever hit it relative to the body that shed it, but it's still moving super fast to anything else in that orbital region. It might leave at just a few meters per second, but something orbiting at a different angle might still plow into it at several thousand meters per second, and the subsequent debris of that collision hit yet more things, shedding more debris and so on. But in a big Lagrange point volume, nothing is keeping any debris in. It will fly or meander out without effort to keep it in, while nothing inside that volume is moving, except for ships or transports, which can operate at much lower speed and which might simply pull on tethers inside that volume, saving fuel and giving you momentum you might use for station keeping larger facilities there. Indeed, moving cargo around on tethers in general is a good way to do station keeping. On that topic, since the moon's gravity is so weak that we can make lunar space elevators to its L1 and L2 points with Earth out of mundane materials, you could do a large diamond running between the lunar L1, L2, L4, and L5 points, and with the moon at the center, and with tethers to each place from the moon and each other. And it would be very easy to do station keeping simply by running mass off the moon as you exported material to those Lagrange hubs to build space habitats, or refill fuel depots, or to move people and cargo around too, of course. So these gigantic extended Lagrange points each have more volume to stably develop in than planets, and indeed are a good deal larger when we're looking at bodies where the moon is smaller or where the distances are greater, like with the solar Lagrange points with planets. But we also get this wider diamond, which I will go ahead and name a Lagrange diamond. Places where you can interconnect things and not need to worry about all the tight and high-speed orbits close to a planet or a larger moon. This is also a place where you can be running very long launch ramps, tethers, mass drivers, and rotavators out of to assist in launch and in capture. Though as a minor note, these Lagrange diamonds would not have exactly flat edges. One trick you can do with a rotavator or rotating skyhook in deep space is to have a tether whirling around out from a large space station, which can be spun out to have a desired tangential velocity a passing spaceship could be matched with, and then the tether can link up and begin winching them in on a decreasing spiral. The space station loses some angular momentum spinning that tether out, and may gain or lose momentum on connecting to that ship or cargo pod, winching in that tether after it hooks up, but should have no problems balancing those out between captures, and even if it needed to occasionally burn some fuel to correct a growing imbalance, it would be trivial compared to total savings. It can also launch ships this way. Fundamentally, what's neat about Lagrange points in this context is that it allows you to build huge conglomerations of structures near a gravity well, like Earth or some planet or moon we're mining, and yet without the problems associated to low or medium orbit where everything is crowded and high speed, where it's causing light pollution or wrecking the view of the night sky, and where there's no threat of Kessler syndrome and no construction problem associated to very large megastructures where they have a lot of different gravities pulling strongly in different directions. That means we can build very large megastructures, like the O'Neill cylinder or even bigger, and in multiples, without the problems of gravity or debris cascades, while not being far from the Earth. Indeed, just 1.3 seconds for signals to go either way, which makes real-time communication possible to both Earth and the Moon, if a touch irritating for casual chat. The upside is there's so much room for development there, and reasons to develop there, that you would have plenty of people to chat with. Indeed, in many ways, these Lagrange points and our Lagrange diamond are in a position to house far more people than Earth itself. and around other planets in a more distant future might tend to be where a large portion of a given planet-moon system people lived, especially if neither body was all that appealing for terraforming but very good for mining. Ultimately, our future in space is a big and spread out one, but there are places that will be highly valued, like planets and moons and the Lagrange points or geostationary orbits around them, and they are essentially the fertile river valleys or deep water coves for space, where settlement will begin and where mighty new realms will arise. We were talking about how to build lots of adjacent space habitats today at Lagrange points, and an alternative approach to that is to build a very long and skinny megastructure known as a topopolis. And one neat feature of that is how they would tend to have one very long river running down them, which might run thousands or even billions of miles long. We'll be exploring that in our upcoming February Nebula exclusive, Topopolis, the Eternal River. And if you haven't already caught January's Nebula exclusive, Giant Space Monsters, that's out now exclusively on Nebula, our streaming service, where we'll discuss what science tells us about all the crazy space monsters we might see on alien planets, or even in the void of space itself. On Nebula, you can see every regular episode of SFIA a few days early and ad-free, and all our other bonus content, including extended editions of mini-episodes, and more of our monthly Nebula exclusives like the Fermi Paradox, Hermit Shoplifter Hypothesis, Ultra-Relativistic Spaceships, Dark Stars at the Beginning of Time, Life as an Asteroid Miner, Nomadic Miners on the Moon, Space Freighters, Retrocausality, Orc-OR and Free Will, Colonizing Binary Stars, and more. Nebula has a ton of great content from an ever-growing community of creators. Using my link and discount, it's available now for just over $2.50 a month, less than the price of the drink or snack you might have been enjoying during the episode. When you sign up at my link, go.nebula.tv/IsaacArthur and use my code IsaacArthur, you not only get access to all the great stuff Nebula offers, like Giant Space Monsters and Topopolis, the Eternal River, you'll also be directly supporting this show. Again, to see SFIA early, ad-free, and with all the exclusive bonus content, go to go.nebula.tv/IsaacArthur. This weekend we'll explore conformal cyclic cosmology and the possibility that a previous universe may have existed over which ours is layered on top, before we head into February to look at death worlds and surviving on ultra-dangerous planets. Then on February 8th we'll examine homesteading in space and what might draw pioneers to new colonies and what sorts of life challenges they'd face. Then on February 11th, Sci-Fi Sunday, we'll ask what might make a civilization quarantine an entire planet and how that might be enforced. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content like Giant Space Monsters at go.nebula.tv/IsaacArthur. As always, thanks for watching and have a great week.